All right, we are moving on to chapter 9. And these upcoming chapters will be fairly short in terms of what we really need to know for a quiz. So chapter 9, which might not be 9 in every book, is called Prime Numbers. Maybe we can't see very well with this window, although the sun is nice. Prime numbers. So prime numbers are very simple to understand. It's simply a number greater than 1. So 1 is not included. Number greater than 1. And the only divisors, no, not divisors. Divisor can be anything. Whoops, what's my undo button? Undo. Don't have it programmed yet. The only factors, that means divisors with 0 remainder, only factors are 1 and the number itself. So let's list the first few prime numbers. No, it has to be greater than 1. Yes.
I'm just confused about the chapter. I thought common factors and multiples were now chapter 11.
Just to confuse people less, I'm referring to the book that you currently have in front of you, which is 9. 9.
Factors and multiples.
Is that not what I...
9 is prime numbers.
Yes. I know if you look at the website, it's actually 10.
Okay, 10. Yeah.
But whatever you see in front of you is what I'll refer to. Since quiz 3 is on part 3, regardless of the chapter numbers, part 3 is quiz 3. They could be numbered 100, it's still part 3. So it really doesn't matter, it's more the topics. But we'll go over the quiz a lot. No need to be concerned about that. Prime numbers, whatever the heading, whichever chapter has the heading prime numbers. First prime number, 2. 3. You're gonna really let him do all of them?
5.
Oh no, she's moving in. So now as you go, we'll do a little more, but I want you to feel how it slowly becomes more difficult to be confident in the numbers you come up with, right? What is the next one? Not 9 because it's divisible by 3.
11.
So we have to go all the way to 11, so making a bigger jump. 12, so obviously any even number now is out because it would necessarily be divisible by 2, which is a number between 1 and itself, and that's not allowed, right? So even numbers are out past 2, but just because you're odd doesn't mean you're necessarily a prime number, but the next one is in fact 13. 15? No, it has a couple. 17 would work again, but it is slowly getting a little more. I can be sure, I just need to think about it a little bit to be sure, because the bigger my number, the more options I have for possible factors. And I need to check that there are none between 1 and the number itself. Next one? 19 does work, so I don't have a lot of jumps there. Not 21. 23. Next one. I have to go all the way to 29. And of course I could look these up, but the point is to see how hard is it to decide for myself. Next one. 31 works. So sometimes they're sort of consecutive. I don't have even numbers as an option, so the consecutive odd numbers are the best I can do. Sometimes the jump's a little bigger. What's the next one? 33? No. 35? No. 37? How sure are you? Is it coming less? No, Google is not How I get sure.
Positive. Final answer.
Final answer. It is getting more and more difficult. Right. So for our purposes, I think it's sufficient if you know up to the 30s. But if I keep going, it's going to get a little more difficult, right? To be 100% sure. Because the bigger the number, the more options I have to check and make sure there are no other factors. I have a lot more divisor options. So the questions, now the Greeks were one of the first people to really look at these numbers, and their obvious question was, okay, well, if I want to keep going in my list, how do I find all these prime numbers before I ask other questions? That's the first question. So I guess I have two versions of the same question, really. One version is how, that was supposed to be a W. How do I find more prime numbers? Because my confidence is now not that good anymore. And given a number higher up, let's say 331. I checked my divisibility tests, but is that enough to know whether it's a prime number or not? How do I? No, the answer is no. How do I decide? Because if I have a large number, bigger numbers could be divisors, and I don't have tests for them. I only have tests for up to 11, but not even all of those, because 7 is not very nice. How do I decide if it's prime or not? So that's really kind of the same question. We'll see soon. It's kind of the same thing. And that is definitely the first question. My confidence is leaving me, so I need some logical reasoning to step in and compensate. Okay. Now, one of the first people to do this was Greek. I guess I can't call them mathematicians. They were philosophers, they were politicians, they were everything. By the name of Eratosthenes. Around, was it 275 BC? I think he was born there. He came up with a method of taking all numbers that I'm interested in. Let's say I want to go up to 400 and find all the prime numbers. Let's take the numbers 2 to 400, because I know 1 is silly. That's not part of my list. And let's come up with a method that sort of sifts out everything else that's not a prime. Everything else can fall away, and only the prime numbers will be left. So we call the method the Sieve of Eratosthenes. A method to sort of have that sifting process, and all the non-prime numbers will fall out. How did it work? I will go to a website, one of many. I'm just gonna get out my mouse because it's gonna be a little easier than that touchpad. So let's suppose we want to go to, my mouse gonna work? Do I have a mouse? There, I can't see the mouse. Let's suppose I want to go to 400. As long as I can still see. Can everyone sort of still see those numbers? If not, we can not shed some light on the subject. We can have some mood lighting. Is that better? Worse? Worse?
Yeah.
Really? Okay. Either way, let's just. I don't want the list to be too short, but I also want to have some room to move. So if we can do 400, that'd be ideal. Now, how did it work? Well, first let's pick a color. Let's go with red. First thing to do is, I know 1 is not going to be a prime number. First thing to do is I'm going to select my first prime number, which I know is 2. And once I do that, all the multiples of 2 are necessarily out. They cannot be prime numbers. So it's sifting out all multiples of 2. It's not going to happen because they will have a divisor, namely 2, between 1 and themselves. Okay? Does that make sense? All right. Now we'll speed this up a little bit because this is going to take forever. Ooh. Come on, faster, not slower. There we go. No. There we go. Didn't know which way was faster. Now let's blue, dark blue.
Yeah, dark blue. Oh.
Oh, we're gonna get through all of them.
Magenta.
We'll get to magenta. So now the next number not colored in is the next prime number, 3. And when I select 3, I'm going to remove all the multiples of 3. You'll see some of them, like 6, it was already sort of sifted out. It was already red. 3 doesn't really eliminate it as a new number that should go, but all the ones that are completely blue, those were numbers that weren't sifted out from looking at 2, but they are multiples of 3, so they need to go. So I'm losing a lot of multiples, I'm losing a lot of numbers once I pick a prime number and all its multiples need to go. Okay, everyone with me?
Mm-hmm.
All right. Then the next number that's not colored is 5. That's my next prime number. He said magenta. Let's do it. Once I select it, all multiples of 5. Some are already removed, 10, 15 already, 20. But there will be some that are completely magenta and need to be removed. So I keep doing that. Oh, that's good enough. It's a nice speed. Keep doing that. Making sure all multiples of 5 are removed. Some new, some were already gone. But there are many that are new. All those that are completely that don't have a red or a blue in them, they need to go out, and I need to consider 5.
Yellow.
Yellow, she says. So the next number in the list is 7. Let's think about 7 first. If I know 7, yeah. If I click on 7 and I color it yellow or highlight it as a prime number, now the multiples of 7 will get eliminated. But many of those multiples are already gone. 14, it's gone because of 2. 21 is gone because of 3. 35 is gone because of 5. What is the first multiple of 7 that is not eliminated yet?
49.
49 is the first one. So keep an eye on 49. Where's my mouse? Cannot find the mouse. There it is. 49, some will be eliminated, but it's not really new. 49 is the first one. That is completely yellow. And after that, more of them can happen. I'm only interested in what is the first one. There are some other new ones, like 259, 119, and so on. But the first one was 49. Color? Pink. Ooh, can I see pink well, though? It looks very purplish.
Okay, then do
Maybe something different. Maybe green. Now, I'm going to slow this down a little bit. The next prime number, of course, is 11. When I select 11, what is the first multiple of 11 that is not yet eliminated and now will be completely green? Not 11 times 2, not 11 times 3, not 11 times 4. Why not? When was 11 times 4 eliminated? By looking at 2. 11 times 5? No. 11 times 6? When was 11 times 6 eliminated? 2 first. And then 3 just backed it up. 11 times 7? No, that would have been gone when I looked at 7. 11 times 8? 11 times 9? 11 times 10? 2. 11 times 11 is the first one. Because the factors in that are only 11. So let's look at where is 121. There you are. Click. Oh, that's very slow. Too slow. Come on, speed up. There you go. There's 121. The first green multiple of 11. And then there are others. I don't really care about them. Care about the first one. All right. Let's do one more color. Orange. Next prime number is 13. First number that needs to be eliminated. That's not yet. Why 169? Where does the 169 come from? 13 times 13. All these have already colors, other colors in them. 169, 169. There you are. First orange one. Now the question is, should I even bother with 17 and its multiples? What is 17 times 17? Because now I know that is the if I pick 17 and I give it a color, I'm running out of colors, but if I do, 17 times 17 is the first one that is going to be eliminated from the list that's still there. What is 17 times 17? 289. No, it can't be. 289 is still in my list, so I need to consider 17. I'm running out of colors here. Which color would work? Light blue, this one?
Yeah. I look more like a teal.
Sure.
Alright, let's get real discussing the colors here.
That's much more important. Discussing the colors are way more important. 289. I needed to consider 17. So I'm only interested in that first one. Do I need to keep going? Do I need to look at 19?
Yes.
Why? 19 times 19, 361 is still on my list. That's the problem. It's not obvious to everyone. I have to think about this. What color, though? It's a tough one. I think this blue is my only real option.
I mean, there's a pink there too.
I can't even tell the difference between these two.
The bottom pink.
Yeah, I'm going to go with this blue. 19, 361, where are you? You're sitting over there. Yeah, there's some nice patterns, yeah. 361, first one. Now, I have sifted out a lot of numbers, and the uncolored ones are potentially prime numbers. Do I need to look, the next prime number is 23, which we know.
Yeah.
Do I need to consider 23's multiples? No, because the first one is 23 times 23, which is over 400. So I get all the white ones are prime numbers. And I get all the prime numbers going up to 400. And all I needed to consider was prime numbers up to 19. So I get a lot for not that much work.
So are we going to be allowed to do this on the 10th?
So when it comes to test questions, this is the method, but we can take from this one important thing that answers our questions. Okay, so first we have to understand how the sieve method worked. What's that line doing there? Okay, any questions on the Sieve of Eratosthenes? Right now, you just want to have an idea of how it worked, and the name might be nice. So, that really answers the question, how do I find more prime numbers? Now, doing that by hand is extremely tedious, and of course not something we can do in a test. So we want to use this idea and answer the second question. Given a number, how do I decide if it's a prime number or not? Now think of that huge table. If I give you a number under 400, what do I really have to test? I only have to go up with a few prime numbers, and if it's not eliminated by then, it's not going to be eliminated. So here it is. I'll do it in general, and then we'll see specific examples. Given a number, let's call it big N. How do I decide if it's prime or not? I need to test divisibility by 2, 3, 5, 7, 11, and so on. And I know, for example, if my number was like 293 that I need to test, it would appear in that table, and I know there's no way I'm going past checking 19. So I'm going to stop at some prime number, let's call it P. That's my stop. These are all prime numbers. I don't need to check prime numbers. When do I stop? Where P squared, P times P, is less than or equal to my number. If my number was 400, I only check up to 19. I don't need to check 23, because the first thing that could possibly not be prime is 23 times 23, and that's way past my number. If it's not eliminated by looking at these smaller ones up to a point, there's no way it can be eliminated. So this is how we do it. Only prime numbers. You can test more, but they're going to be completely pointless. Why do I not test 4? Divisibility by 4. I have a test and everything. If it's a yes and it's divisible by 4, it would be divisible by 2, and it's pointless. It would have already been done. So only the prime number divisibility need to be tested. Now, of course, once I go past 11, I don't have tests anymore, but you have a calculator to speed it up in case you go that far. You do need to know where to stop. So let's do exercise, whatever the first exercise is. 10.1, 9.1, the first one. In your book, it might be 9.1. If I update the book and correct the chapter numbers, it will be 10.1. Regardless, I have to test 682. Prime, yay or nay? Nay, why not? So we want to give a yes-no answer and a reason. It's divisible by 2. And my divisibility test checks that very easily. So some can be that simple, yes. Okay. And I didn't need, I did do the divisibility method. The first one just happened to already be giving me my answer. So there wasn't much to do. 71. Prime, yay or nay? Now I have to test. Test divisibility for 2. Nope, so I keep going. 3. No, because the sum of the digits is 8. 5, definitely not. 7 is next. No, because 70 would be a multiple. Where do I stop though? Do I need to check 7? 7 squared is 49, which is under my number, so yes, I did need to check 7. Next one is 11, but 11 squared is 121, which is greater than my number, so I can stop right there. You can check 11. 9 is not a prime number. Oh,
No,
right. As in, no, it's not. No, it is a prime number. Because everything I checked in the list that I should check give me no. So 71 is not a multiple of the important prime numbers. And I don't need to check further. So yes, it is a prime number.
9 is a prime number? Okay, what?
71.
No,
You
I
said
said
nine?
9 is not a prime number. Then I thought you said a fancy no.
Okay.
So I got it.
Okay, we're good. Yeah.
Yes.
How is that? Like, it makes sense why it's conclusive, like evidence, but like, why is it conclusive? I just don't really.
Because the Sieve of Eratosthenes.
Yeah. Okay.
If where is it now? A little bigger. If my number is somewhere, let's say it's this guy, 337. Let's suppose the number I'm testing is 337. It doesn't come out when I test 2. So testing for divisibility is the same as checking the multiples. It doesn't come out when I check 3. It doesn't come out when I check 5, 7, 11, 13, 17, 19. Nothing catches 337. So if I now keep going to my next prime number, which is 23, the question is, does it make sense to even check 23? If 23 divides into 337, it's going to be 23 times something. It's going to be 23 times something small because the number's not that big. If it's 23 times 2, I would have caught that already by looking at the other smaller one. So the first one the size of the number that I need to consider is in the range of 23 times 23. But that's way beyond my number. So there's no point. So you can definitely check them, but they will never give you a yes if you didn't catch that already. So it's using the same argument, but it's not exactly the same. The same principle. Any other questions on the procedure to find yes or no? Often people in tests do strange things. They test everything that they have a divisibility test for. And if that's a no, they just stop. But just because I didn't bother with divisibility tests for bigger numbers doesn't mean they don't exist. Doesn't mean I shouldn't check them. There are divisibility tests for 12, 13, all of them. We just have to cut it off at some point because we don't really need to keep going. 3. 7, 8, 7, 8, 4, 5. Now this is a big number. There's probably going to be a little trick to find an easy factor, and I don't have to check too far in my list. Prime, yay or nay?
No.
Yay or nay?
Nay.
Why? Divisible by 5. So there's a little trick for us, at least, testing-wise. If the number is pretty big, like thousands and beyond, one of my divisibility tests will probably catch it. And if I see it immediately, I don't have to go through the list. I can just find it. Number 4 is again big. What is happening? Way too big for me to go down the list very far. Prime, yay or nay? Well, let's go through the list a little bit at least, but I know because the number is so big, it's going to be one of my divisibility tests. Just to make things manageable. Not divisible by 2, so I keep going. Divisible by 3? Well, I need to add the digits. 8, 17, 25, 26, so that's a no. Do I check 4? No! 5. No, not 5. I do need to just run through it and show. I do know what to do. 7, there's no shortcut for 7, just divide it. Use your calculator. Do long division if you want to practice. The test for 7 is quite pointless. It's academic at best. No saving. Does it work for 7? No. 11, let's check. It's good practice for the divisibility test. I go right to left, right? So here, my what I call comparison number is 1 minus 8 plus 9 minus 5 plus 3. Right to left always starts with a plus. So that's minus 7. That's 2. That is negative 3 plus 3 is 0. And we know 0 is special. It works for 11. Anything non-zero divides into 0. You can't divide 0 into 0 because series says so. So I found one. I found a factor. So that is not a prime number. It's divisible by something in between 1 and itself. There is a number 5 on the other side of the page, a little hidden, but it is there. 667. Prime, yay or nay? It's right in that range where I don't know, so let me just go and test my numbers. Prime numbers only. Divisible by 2? Divisible by 3? Well, if you check some of the digits, 12, 19. No. Divisible by 5? Obviously not. Divisible by 7? I just do it. 7 goes into 66. 9 times with 3 left over, leaving 37. No. Next one is 11. Comparison number is 7 minus 6 plus 6 is 7. That's not going to work. Am I going too fast? I don't know.
Yeah.
Where did I lose you? 2? 3? Surely not 2. 2 is okay. 2 okay? 3? I have to add up the digits and they don't work. 5, I just look at that last digit. That's a no. 7, there's no real shortcut that's worth it. So I just do the division, and I quickly do it in my head because I'm only interested in the remainder and I don't have a calculator on me. What? It's long division is not boring because the word long is in it. It's not yawn worthy.
Oh no, that would be
7 goes into 66 9 times for 63, and then I have 37 left, and that doesn't work. So I keep going to 11. My comparison number in 11, or in the case of 11, is right to left, 7 minus 6 plus 6, but that's 7. And 11 doesn't go into 7. So that's a no. I don't have any more divisibility tests. Do I stop? No, I don't stop. Because 11 squared is only 121, well under my number. Next one is 13. Now sure, use the calculator, perfectly fine. I do need to check 13 because 13 squared is still... It's nice to memorize some of these. They sort of happen naturally up to 20. 169, well under my number. Next one is 17. Do the division. Does it work? No? Did I need to check it? No, we said that was 289, didn't we? Well under. So I do need to keep going. Running out of space here. 19. Do I need to check 19? Yeah, 19 squared is 361. I just memorized them. So I do need to check it. Is it a yes? No, no, it's also a no. I need a yes to come. I'm running out of space. Next prime number? 23. Do I need to check 23? 23 squared is what? I did a lot of these. You can do one. 529? For some reason, regardless of how much I try, I just cannot memorize 23 squared. I always doubt myself. Don't know why. Anyway, so I do need to check it. It's under 667. Is it a yes or a no for divisibility? Yes! Thank goodness I found it because I had no more space. So is it a prime number? No, it's not, because there is a divisor, a factor rather, that is between 1 and the number itself. But see how, I like this example because it shows that you can't just rely on your divisibility tests. You have to go as far as that prime factor squared requirement takes you. Any questions on when to stop checking?
When the square becomes higher than
When the square of the prime number is higher than the number you're testing, there is no way it'll be a yes. If you haven't found a yes by then, it's a prime number. It has no other divisors. Now, okay, this is interesting, I suppose, but what is the point? Oh, there's one more here. Sorry. Before I get to the actual point, there's one more exercise. Exercise 9.2, 10.2, whichever one you look at. True or false? True or false? The largest prime number p, such that p squared is less than or equal to 1,000, is 29. Now, first of all, we need to understand that statement. Perhaps a little mathy. So that's our requirement. We're pretending we're testing a number close to 1,000. We make a list of our prime numbers. Really, mowing the lawn, I'm recording. So insensitive. We are making a list, we're checking it twice. No, it's still Halloween still. That's not right, sorry. Know your holidays. And we're gonna go up to a P so that I go as far as I can, but still under 1,000. Is that P 29? Is 29, what's 29 squared?
841.
841. So definitely it is under 1,000. But what's the next prime number? 31.
Squared is 961.
And 31 squared is 961, she says. So that's still under. And then the next one? Bleh. 37, we said. That's way too much. So that is the largest one. So this number is larger than 29. So that is the largest prime number where the square still falls under 1,000. So it's just another spin. I won't put a question like that on the quiz. It'll be straightforward. Here's a number. Decide if it's a prime number or not. And explain why you're saying yes or no. That'll be the question. Nothing else. All right? Now, moving forward, what is the point of prime numbers? What is the point? It's fun, perhaps, to some. But if there's no point, then it doesn't really have a lot of meaning in general. Turns out there is a very important point. There are two significant results that came from the Greeks studying these prime numbers. Now, in the book, I provide an explanation of how it would look to prove these results. They're not the simplest thing ever. I do use something called the principle of induction. That is not inductive reasoning. It's just an unfortunate coincidence, if you were to read this. But I will never ask you to prove these. You do, however, have to know them. Which one do I state first? Okay, yeah. I'm going to do them backwards, actually. I'll list this one first. There are infinitely many prime numbers. If you have nothing to do, I strongly encourage you to see how they get to that conclusion. It's very interesting. One of the most fundamental results ever. That the prime numbers never stop. If you think you have the largest prime number, there's another one after that, and another one after that. It never stops. And many people are dedicated to just finding larger and larger prime numbers. And a lot of security, credit card security, a lot of things like that are built on very, very large prime numbers. And finding them being super hard as anything. If I give you a large enough number, I'm talking hundreds of digits, it'll literally take you forever to figure out if it's prime or not. If I just make it big enough. Forever. There is no shortcut. But I can always find a bigger and bigger number. So it's a problem some people are very interested in. And a lot of our online transactions and security are based on prime numbers in a more complicated way that I can really explain here. The other thing is that, which one should I say first, the informal or the fancy one? I'll do the fancy one first. Not super fancy, but any number, and I now specifically mean whole number, but I'll just say number. We don't mean fraction or decimal or anything like that. Any number can be written as the product. What does product mean? Product means one thing in math. Multiplication. Product of prime numbers. In English, the product means different things, but not in math. So, for example, let's take 100. 100 can be written as 2 times 2 times 5 times 5. Any number I can do that with. I can split it up into the multiplication, the product of prime numbers. Any number. So in that sense, these prime numbers can be seen as the building blocks of all numbers. And if we understand how prime numbers behave, we understand everything. So instead of analyzing 100 and seeing what it can do, how good is it, how useful is it for whatever needs I have, it depends on how 2 and 5 behave, because they make up 100. Now we write this in a short version, 2 squared times 5 squared, but it's the same thing. Exponents are just repeated multiplication. So whichever one you prefer, I don't care at all. Any number can be written as the product of prime numbers. And there are infinitely many of them. So there is no limit to any of this. That ends that chapter. See, very short. Let us quickly talk about the problems. And then tomorrow we will move on. I do have a section. Let's do the problems first. I like them all. In your book, page 88, problems 9.1, 2, 3, and 4. I like them all. There is a section after that problem set, talking about the divisibility of other numbers like 13 and 17, and they actually have divisibility tests that are very similar to 7. Interesting, but sadly not that useful. But it is there if you are curious.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos.